suspension. We are looking forward for your talk.
Thank you very much. I shall present some results of our research group from the University of Iași, Romania, a city not so far from here, but it took a while to arrive here by car with my friends. In the meantime, we had the opportunity to see how nice the people is around here, helping us to reach this wonderful book of it. So it has to be said that magnetic nanoparticle stable suspensions are also known as magnetizable nanofluids or magnetic fluids or ferrofluids, and basically they contain nanoparticles with magnetic properties suspended within a carrier liquid, and they are designed to be used in conjunction with magnetic fields. They could be stable for some time, depending on the third ingredient, the coating shell of magnetic nanoparticles. And this is something that we try to do, and maybe we succeed in some respects. We have prepared, and we shall present to you some data regarding the fluids, the stable suspension of magnetic nanoparticles for technical utilizations based on magnetite or iron and other metal oxides dispersed in liquid hydrocarbons, as well as some other arrays of magnetic nanofluid stable suspensions based on magnetic nanoparticles and water as carrier fluid for biological applications, biomedical applications. We need to mention the well-known utilization as contrast agents in magnetic resonance imaging, but not so much spread yet. The experimental cancer treatment with magnetic nanoparticles and based on magnetic hyperthermia, and magnetic targeting and controlled drug delivery. So the issues of stability of such soft magnetic materials, like the magnetic nanoparticle suspensions, are dealing with the three main aspects that are mentioned here: the stability in a magnetic field gradient within the gravitational field, and the stability against magnetic dipole-dipole attraction. As the theory is telling us, and as summarized by Rosenzweig, the father of magnetic fluids, the main condition that was formulated from theory for the diameter of the magnetic nanoparticle regarding the stability in magnetic field gradient first is that such a diameter remain smaller than 8 nanometer. At the same time, the stability in the gravitational field is practically ensured for a certain amount of fluid contained within a laboratory vial, since for pure magnetite the magnetic energy is higher than the energy of gravitational attraction. So the condition is practically fulfilled for pure magnetite, while the third aspect regarding dipole-dipole attraction leads also to condition for the magnetic core diameter this time, since we are dealing with magnetic colloidal particles after all, and this is the requirement that this magnetic core diameter is smaller than 7.8 nanometer, theoretically for pure magnetite and for spherical particles. So generally, if we have an average diameter smaller than 10 nanometers, we hope to get a stable enough fluid to be used for various applications. We shall succeed to prepare some magnetic nanoparticles stabilized with oleic anion in liquid hydrocarbons by applying two methods: conventional chemical route or chemical coprecipitation, and then mechanochemical method or wet milling technique. And then we have succeeded to stabilize some magnetic nanoparticles in water by chemical coprecipitation, and using as the third ingredient the coating shell of the magnetic nanoparticles, different organic molecules. The coprecipitation method is, I believe, very well known, and however, it is also still available for low cost and still leading to a rather well distribution histogram for the diameter of the particles. Here are the ingredients and the main steps of the procedure. Here is a more detailed scheme of the coprecipitation method that we use, starting from the report of Massard since the ages and with some adaptation. Some details regarding the amounts are presented here, the temperatures, the timing, and the washing for removal of the residual products. Other details could be seen in some of our published papers, since there are some adaptation to the classical method. The wet milling, or the mechanochemical method, is starting from the ferrophase already prepared of a micrometric size, like those resulted in the charcoal industry as a residual, but rather pure from the chemical viewpoint. The oleic acid and the kerosene are added since the beginning together with this micrometric ferrophase. And then we have to wait the milling process as long as we need to get good results. This could be a disadvantage, but I believe it is balanced by some advantages regarding the good results that we have obtained, and from the environment protection viewpoint, no chemical spread it within the laboratory, and no external heat source needed, because the wet milling involves the strong collisions between the steel balls with the magnetite microparticles, process during which high kinetic energy is released, and it is able to favor chemical adsorption of surfactant, the oleic acid in this case, to the nanoparticles, and to provide a good stable ferrophase suspended in hydrocarbons. Here are some results. First results, comparison between the samples prepared by coprecipitation methods and those prepared by wet milling. Transmission electron microscopy showed rather convenient distribution curves with the diameter of highest frequency appearance smaller than 10 for the first method, smaller than 8 for the second method, with quasi-round particles and even quasi-round large aggregates, as shown by the atomic force investigation, with lower accuracy from the point of view of the smaller diameters visualization, but with the advantage to let us see the topology of the particles. Are those large aggregates actually present in our native fluid, or are they only the result of the drying process during sample preparation for the scanning microscopy? The answer was given by small angle neutron diffraction. Our colleague from Hungary, working at that time in Switzerland, was able to do this analysis, and the result is no, they are not present within the native fluid. So that the highest nanoparticles with rather low frequency are no higher than 20 nanometers. The main parameter for discussion of stability is the diameter of higher frequency appearance, and this one is small enough in both cases. And the same time, crystallinity was rather good in both situations, with specific peaks of spinel structure. Some artifact resulted from liquid traces within the preparation sample, so that the so-called zero line is not so horizontal. The diameter of the crystallite was measured in all cases, and from the magnetization data, the largest magnetic diameter was also evaluated according to Langevin's theory. Higher magnetization was obtained for the wet milling product, and this is of course because during the long milling time a higher amount of ferrophase was incorporated within the fluid. Other studies that we began to do in collaboration with Dublin Ireland Catholic University regards concern the complex susceptibility, and the first results show that according to the theory of magnetic relaxation, with nil relaxation versus Brownian, one could lead to the hydrodynamic diameter of the aggregates that are formed when the frequency critical value is about this 2 kilohertz. So the hydrodynamic diameter is no higher than 37 nanometer. Some biotechnological applications were proved to be possible with those magnetic nanoparticles suspended in hydrocarbons in kerosene. Not biomedical application, because for the medicine, for the human body, we need always aqueous or water-based fluids. But for the stimulation of some in vitro culture of plant tissues, and for the stimulation of some cellulolytic fungi like the fungus Scedomyx globosum, in this situation we succeeded to prove the utility of such ferrofluids. This fungus is rather important for the environment protection issue, since it is able to degrade wood waste from wood industry that may pollute the environment. The second category of fluids with magnetic nanoparticles suspended within them that we approached are those one with an aqueous environment for final the product, not only magnetite but zinc ferrite also, and cobalt ferrite stabilized with oleate ion also, but from sodium oleate, which is hydrophilic, in contrast with the oleic acid, which is hydrophobic, of course. Ferrophase preparation, and the main reaction phases: first hydroxides formation and then oxides precipitation. And here is the long tail of this water-loving molecule or ion, which is the oleate, ensuring a good covering of nanoparticles with this non-magnetic shell, but hydrosoluble and also biocompatible, as some literature data have shown. Here are the results for the X-ray diffractometry. In all cases, a typical structure of spinel and no other supplementary peaks, no peak missing. Here are the magnetization data with no hysteresis, meaning supermagnetic behavior, except this cobalt ferrite, and this was because of higher particles and earlier agglomeration that we found by atomic force microscopy. Even from the other methods of diameter estimation, magnetic or transmission electron microscopy, it was shown that particles are higher than for the other particles. So we have to work more on this method regarding the details for optimization. Some applications that we have already done are regarding the impact of such magnetic nanoparticles on plants, or on it's better to say on plant embryos. Sunflower, for instance, exhibit genetic impact following the administration of the magnetic nanoparticles that we prepared, and were supplied in small concentrations up to 200 microliter per liter, comparable with those concentrations resulted from manufactured nanoparticles produced by so many nanotechnologies to improve human life, but when they are released within the environment, water, soil, air, they could be polluting. We invite you to see the genetic impact of these nanoparticles in the afternoon to our poster presentation. The other category but the magnetite nanoparticles stabilized in water was focused on the nature of the organic coating shell. Citric acid and tetramethyl hydroxide are also known from literature. We prepare those fluids to have a comparison reference, and also sodium oolate, but the main goal was to see if some antibiotics or other molecules with medical interest could be directly attached and not grafted on the coating shell as usually is done. Here are the amounts of the molecule used to coat the nanoparticles. There is also a cyclodextrin that we studied. Why rifampin and why cyclodextrin, I am trying to tell shortly. This is a strong antibiotic, very useful in lung disease treatment. But being a strong antibiotic, at the same time, it affects all the other cells of the body. So it will be better to be targeted directly to the lung. This could be done with magnetic carriers, like the magnetic nanoparticles we prepared. How to attach it to the magnetic nanoparticles? The computational modeling revealed that there are some sites where it is an increased density of a negative electric charge, and actually we believe that on this site, the cations from the magnetic nanoparticles were attached. Why cyclodextrin? It is so well-known carrier molecule by its specific and amazing properties to be hydrophilic at the external wall, while it is hydrophobic to the internal wall. So we tried to attach nanoparticles to its external wall and to use the hydrophobic properties of its internal wall to form an inclusion complex with tetracyclines. We are going to publish some paper regarding chlortetracycline inclusion, chlortetracycline that was reconsidered now not only as an antibiotic but also as a possible treatment for cancer. So we shall present some comparison between those fluid preparation and results. Here are some considerations regarding the two types of stabilization of nanoparticles within the carrier fluid. Except the tetramethylammonium hydroxide, where electrostatic stabilization is the main physical process, ensuring the repulsive forces among colloidal particles, able to balance the attraction forces between magnetic dipole-dipole. In all other cases, there is a steric stabilization with the water-loving molecules with molecular sites able to receive cations from magnetic nanoparticles. Here are the transmission electron microscopy data and histograms. In some cases, the highest frequency diameter is around 10, but generally smaller, 10 nanometers. Here are also the atomic force microscopy data in three-dimensional view or in phase contrast and phase recording view, all over only quasi-spherical particles or some large aggregates in some time. Sometimes here are the results of X-ray diffraction data with crystallinity specific spinel structure, and here are the magnetic magnetization curves. Low magnetization, saturation magnetization for cyclodextrin, but rather good saturation magnetization for rifampicin coated nanoparticles compared to those nanoparticles coated with sodium oolate. So we concluded that for cyclodextrin, the attachment process to the magnetic nanoparticles, it's not very well controlled, at least in our experimental work, so we need to focus on this in the future. Some applications that we have done regard the putative side effects of magnetic nanoparticles used in biomedical investigations, such as in the case of contrast agents for magnetic resonance imagistic. in the human body there are low levels of pathogen germs inside of our intestinal digestive tube, and others such as Staphylococcus aureus or E. coli or the Pseudomonas aeruginosa, and we found that this one can be stimulated for low levels of magnetic nanoparticle suspensions supplied within the body, comparable to those used actually in the biomedical investigation. And we have published some of these results. In the final part of my presentation, some words about the manganese, zinc, and iron nanoparticles coated also with the oleatine from a sodium oleate molecule. A series of products with increased manganese content from 0.3 to 0.9 were prepared and characterized. Here are the crystallinity data. All of the same spinel structure, whatever the manganese content was, except for the magnetization data, where progressive coercive field was evidenced to the increase of manganese content. It was some correlation between the coercive field and the crystalline size, as well as between the saturation magnetization and the crystalline size. And another group where our colleague Nika Valentin was working was able to demonstrate some interesting calorimetric properties of these fluids that recommend them as cooling fluids for the industrial devices for where heat in large amount is released. And finally, the new fluid that we are going to study in the next with ascorbic acid, and with the new investigation method, the zeta potential measurements. It is after 1 year, and it is still stable in some respects. I need to say that generally those fluids in water are stable, at least in our case, for a few months, while the other ones, based on hydrocarbons, were stable for some years. Thank you very much.
Thank you very much for the nice talk. The talk is open for discussion.
I have one question, mostly practical question. I am very interested, what is the sedimentation of the nanoparticles, magnetic nanoparticles, in special fluid which have very low evaporating, used in space, for example, application, when you want to keep the lubricant inside special contact area, very thin layer about 500 nanometers, for example, say. What is the sedimentation of the nanoparticles? Because I want to predict the friction or something like this.
Thank you for your question. I understood it, but I think I am not able to give a satisfactory answer, since we had not dealing with the technical applications. I believe that for those technical applications, a good and stable magnetic fluid dispersed in hydrocarbons is going to remain stable for some years in the presence of magnetic fields that are from the environmental sources or local devices within the spaceship or somehow like this. If the evaporation of the carrier liquid occurs at a certain moment, there are too many particles and less fluid, and sedimentation is expected. But I cannot say how much, because I didn't work actually on this field.
It's not interesting for me. What is the sedimentation because of the substrate?
Because the interaction with the... this is one of the conditions that is actually listed when someone in literature is talking about technical application of such magnetic fluids. Not to interact with the metal or polymers or the other materials where it is going to be used, not to release vapor that are toxic, not to release heat or something. These, I believe, there are specific issues that that every research team that is focused on technical application is able to resolve by itself. So cannot.
Okay.
But
We have time for a short question.
I'm not sure.
Oh, okay. Then let's thank the speaker again.